All right, so let's begin. For those of you who may in the future be watching online or on the video, I know last lecture was recorded in a way that the stuff written on the board was not super legible. I have scoured the Zoom settings and I have pressed various buttons that make the promise that they will they will result in a recording that is bigger, takes more space on the disk. It very carefully does not promise that the image quality will be better, but we will see what happens. So just to like briefly remind us where we were last time and what is, and the sort of broader agenda this was the beginning of. Okay, so we set out this sort of impossible goal of learning the true conditional label distribution. Like ideally, if you show me some feature vector X, I would like to be able to tell you everything possible about the induced conditional distribution on labels. Okay, and in like the binary outcome case 0 or 1, the only piece of information there is what is the probability that the label is 1. Okay, and so this is just the conditional label mean. Okay, and we started thinking about this. And we sort of realized early on that it's kind of hopeless. Like there's no way we're going to be able to learn the true conditional label distribution, even to just come up with the conditional label mean in the binary case, because if the feature domain is very large, like if I've got d binary features, there's 2 to the d feature vectors that might show up, or if it's a continuous space, then there's really a lot of feature vectors. I'm probably not going to see any particular one more than 1 time. Most of them I will see 0 times. And so I have 0 samples from these conditional label distributions. It's just too much to hope for to learn them. And the sort of agenda that we kind of set up was we said, okay, well, I can't learn the true distributional quantities that I'm after, but maybe, as like a second best thing, I can try to think of like basic sanity checks, like basic sort of statistical hypothesis tests that the true conditional label distribution would pass. And, my goal can be to come up with statistical estimates that pass this thing too. Okay, and maybe as we build up more and more sophisticated kinds of tests, trying to falsify that the thing that we've learned really is the true distributional quantity, right? Like maybe then if we can't think of any other way to test, we can't think of any other tests, in the end, maybe, that might have the power to distinguish the thing we've learned from the truth, then maybe we are sort of satisfied with the thing we've learned. That's the broad agenda we've set up. But what we started with last class was, like a really simple, trivial test, which we called marginal mean consistency, which just asked that the average prediction of the model was equal to the average of the label. So if I just average over the distribution of the conditional label expectation predicted by the model, that should equal, on average, the frequency with which the label is 1, or more generally, the average value of the label. Okay, like definitely the true conditional label distribution would satisfy that. And it's sort of like the weakest thing you could imagine, the weakest test you could imagine to check if if this falsifies that our model is the true conditional label distribution. And what we saw is that if you have a model that doesn't pass this test, then number one, it's very easy to fix the model to pass this test. Just shift the shift the mean of the model so that it passes this test. Just like if it predicts on average a conditional label distribution that's too big, just shift its predictions down everywhere. Or if it predicts something on average that's too small, just shift its predictions up everywhere, until on average its predictions equal the average of the label. And what we showed is that not only was this sort of not only was it easy to fix a model to satisfy this basic sanity check, that it was actually sort of a good idea to do so, in that when you did that, the squared error of the model actually went down in proportion to how big a shift you needed. Okay. And sort of the moral of the story here was that if you identify something wrong with your model, okay, some way of distinguishing your model, in this case, a very simple one from the true, optimal model, inaccessible but out there somewhere, that fixing it is only helpful to you. And I sort of foreshadowed that not only would this sort of be maybe like a normative statement, if you find problems in your models, you should fix them, that this would sort of be a technical lemma that we would use down the road to try to pass more sophisticated tests. Okay, but this was all for means, right? This was marginal mean consistency. And there was this nice connection between squared error, or this objective function that we used sort of as a potential function that we said was reduced when you fix marginal mean consistency. But when we start thinking about distributions that don't just have binary outcomes, when we think about more general regression problems, for example, and this will also be relevant when we get to conformal prediction, there are things that we will be interested in about the label distribution that go beyond the mean. So maybe if I ask you to think about statistics of a real value distribution beyond the mean, maybe like the first one you think of is like the median. And like more generally, I can think about quantiles, right? So maybe like if I'm interested in giving a prediction interval, right? If I'm solving a regression problem and I'd like to say, 90% of the time, the prediction that I make or the label falls within this interval of the prediction that I make, then what I'm really interested in is like the 90th percentile quantile of the residual distribution, the difference between the prediction I make and the truth. Okay, this is the kind of thing that when we start thinking about prediction intervals, we'll be interested in. And so what I want to do in the first part of today's class is build up sort of very simple machinery, analogous to what we did last class for means, but for quantiles. Okay, so I'm going to think about, again, sort of a very basic sanity check, just sort of a marginal consistency, check, a marginal quantity averaging over everything. So in that sense, just as weak and silly as what we did last time for means, but for quantiles. And in particular, squared error will no longer be the right potential function for us. We're gonna need some other function that will play the same role, such that when we fix a problem that we notice in our model, that on average it's predicting quantiles in a way that are not consistent with the label distribution, that when we fix that problem, that this sort of metric goes down, right? We need a sort of analog to squared error that will serve as a role, the same role that squared error will serve as a potential function when we talk about means for when we go on to talk about quantile. Okay. So that's the plan for the first part of today, and maybe if we get to it, we'll talk about sequential prediction. But before I begin with definitions and such, are there questions about the basic agenda for the course or anything I just said or anything along those lines? Okay. So let's think about, again, keep in your mind regression problems. Okay, so we'll think about like a setting maybe where you want to think about like the label domain as being, let's say, numbers between 0 and 1, or maybe the whole real line or something. But the point is they're not binary and they're real valued. Okay, so there's some like continuous one-dimensional output space. Okay, so what's a quantile? Oh, and maybe for simplicity, in this lecture, we will assume that the marginal label distributions d of x, remember this is just the conditional distribution on labels, conditional on the features being x. Let's assume that these are continuous. Okay, there are analogs of what I'm going to say, including definitions of quantiles for when the label distributions are not continuous, but it's going to be simpler to think about continuous distributions. Okay, so what's a quantile? Here's a definition that makes sense for continuous distributions. So, when we talk about a quantile, I have to tell you which one, right? It's like a percentile of a distribution. Like the median is the 50th percentile. And in general, percentiles can range from 0 to 100. So let's fix any Q quantile. It's just going to be a number between 0 and 1. Okay, and that's like the percentile of the distribution, the label distribution that we're going to be interested in. Okay. Then tau, also a real valued quantity, is a Q quantile some label distribution if the probability under this label distribution that the label is at most tau is Q. Okay, so a median, a 50th percentile quantile, like when Q is 0.5, is the number such that half of the labels are below the number and half of the labels are above the number. Right, and when it's a continuous distribution, these things actually exist for every Q. But I could also ask for the 80th percentile quantile, Q.8, the level such that 80% of the time the number is below tau. Or I could ask for the 95th percentile quantile, the value tau such that 95% of the time the number was below tau. Okay, does that make sense? Clear? Okay. And so, ideally, right, we'd really, just as when we were talking about means, the ideal case again is that we might learn the correct quantiles for the conditional label distributions for every x, right? Like our target pie in the sky function is the function f star of x that for every x maps to some target quantile at some level q of the conditional label distribution given x. And for exactly the same reason that it was impossible to estimate this for means, you can't do it for quantiles either, just because you don't have samples from these things. But we can write down an entire, the analog of sort of the level 0 sanity check that we did for means, which is marginal consistency. If I look on average over the quantile predictions made by the model, then on average they should exceed the realized label at the target quantile level. That would be true of the true conditional label distributions, and we would like it to be true of our models as well. Okay, so here's the analog of marginal mean consistency that we talked about last time. So a model F, which maps feature vectors to predicted quantile values, has marginal quantile consistency error alpha with respect to particular target quantile. I have to tell you which quantile I care about with respect to a target quantile Q if when I look at the marginal probability, okay, by marginal probability, I mean the probability over both feature vectors and labels sampled from the underlying distribution, the marginal probability that the label is less than the predicted quantile. Okay, well, if f was predicting the true conditional label quantiles, then this would be exactly q. Okay, so to the extent that this quantity, this marginal quantity, differs from q, well, that is evidence that our model is wrong. And if it differs by alpha, then we'll say that it has marginal quantile consistency error alpha with respect to target quantile q. Okay, and just notationally, if alpha is 0, f satisfies marginal quantile consistency. For q. Okay, so is it clear how this is the analog of like marginal mean consistency? Like if somehow we had learned actually the function that really does map x to the conditional label quantiles, then, well, for every x, when we sample y from the conditional label distribution, this probability would be q. And so averaged over the feature vectors, it would also be q. Here, we're asking for something much weaker, the marginal version, where we're averaging over x as well. And to the extent that we have large marginal quantile consistency error, that falsifies that our model is correct. Okay, clear? Okay. So, of course, just as with discovered violations of marginal mean consistency, it's easy to fix violations of marginal quantile consistency. If we are systematically predicting values that are larger than the labels like 90% of the time, but we're trying to predict like 80th percentile quantiles, then we can just like uniformly shift down our predictions. And because it's like a continuous distribution, the probability that our predictions exceed our labels will continuously shift down from 90% to 80%. So we can just shift things down, shift the whole model down to get things right. But what we want in order to sort of get some sense that when doing this, we are making progress, is some analog now of squared error, something that will decrease when we do this. Okay. Let me ask a question that maybe some of you will know the answer to. Does anyone here know what a proper scoring rule is? Or have heard of property elicitation? Okay, so this is a small aside, but there's a connection here. So suppose that, I've got a weather forecaster and I believe that he or she really do know the probability of rain today, but he or she or they are they're not really in it for the love of weather. They've got pecuniary interests. They just want money. And so they're not gonna just tell me what is the probability that it's gonna rain today unless I incentivize them with money. Right? So I want to write a contract. Oh, but like I don't know what the probability is of rain today. Right? So I want to write a contract with them of the following form. They tell me the probability of rain today. Then I step outside and maybe I wait all day and I see if it rained, right? I can observe the outcome. And then I have to figure out how much money I'm going to pay them as a function of these two things, the probability of rain that they predicted and the binary outcome, did it rain or not? Okay. And I'd like to design that contract so that given that the weather forecaster knows that it does know the probability of rain, I'd like to design that contract so that it is in their best interest. It is a dominant strategy for them to report truthfully, to tell me the probability of rain. So you can think about how I might go about designing that contract. Like, for example, maybe I should, somehow pay them in proportion, like the difference between their prediction and the outcome, or the absolute value of that difference. But if you think about that, that would incentivize them to extremize their forecasts, right? Like if I paid them the absolute value difference between their prediction and the outcome, then if they think there's a 51% chance of rain, if it rains, I pay them 1 minus that. If it rains, they make 51 cents. But if they told me 100% chance of rain, then when it rains, they make $1. And if you work out what is their expected payoff, what they want to do is extremize. Now, it turns out that if I want them to report the probability of rain, or more generally, the mean of the distribution that they know that I don't know, then the way I should design the contract is to write down a scoring rule, a payment rule that depends on squared error. Okay, I should pay them 1 minus the squared difference between their prediction and the outcome. Okay, and the reason why this will incentivize them to tell the truth is exactly what we derived last class, that if you work out what is their expected payment, right, in expectation over the realized label, well, it's maximized when they report the mean. If they were predicting anything other than the mean, you could shift their prediction to be the mean and make more money by exactly the square of how much you shifted it. That's exactly what we proved last time. Okay, so just viewing it through your game theory lens, we proved that you might say that squared error is a proper scoring rule, that it incentivizes a proper scoring rule for means. It incentivizes people who know distributions to correctly report, truthfully report the mean of that distribution. So what we want, if we want a similar thing for quantiles, is a proper scoring rule that gives agents a dominant incentives such that it is a dominant strategy for them to report the quantile of the distribution that they know and that we don't. Yes.
We want to be a strictly dominant strategy.
We do, yeah. We'll get into this, but it's like not enough for us, right? So what this lemma that we proved for squared error, it didn't just say that when we fix a problem with marginal mean consistency, the squared error goes down. It said when we fix a problem with marginal mean consistency of magnitude delta, when you were wrong by magnitude delta, the squared error goes down by delta squared. Now, it's not yet obvious to you why this is going to be important, but ultimately, when we try to come up with models that pass more stringent statistical tests, we are going to be sort of making multiple fixes of this sort. And we want to be able to argue that this process can't go on forever, that we don't just keep chasing our tails. And in order to make like quantitative progress, we need that when we fix big problems, we make like quantitatively a large amount of progress according to one of these things. So it's not enough that a minimum is at the truth. It needs to be like the minimum. And in fact, not just that it's strictly proper, but that, the progress is bounded away from zero. That's actually going to be something that comes up just in a moment, because quantiles are more complicated in that way than means are. Okay, but I'm going to define a function now called pinball loss, and if you look into the scoring rule literature, this elicitation literature, it has a different name, but it's a known proper scoring rule for eliciting quantiles. Okay. So, no questions about any of that? So the pinball loss function for target quantile Q is the following. I'll write it as L sub Q, and it takes as input two things. A threshold tau that is, supposed to be like a predicted Qth quantile of some distribution, and like a realized label Y. Okay, so the weather forecaster says there's a 90% chance, Q is 90%, that the number of inches of rain tomorrow is less than 0.23. 0.23 is the threshold, and then it rains. That's y. It's like 1 inch of rain, and then I want to like map this to a score. Okay, so how are we going to do it? Well, it's two cases. Either the realized label was bigger than the prediction, in which case the score we will give this is y minus tau times q. Okay, so the difference between the realized label and the prediction, which is a positive number because the realized label was bigger than the prediction, times q. Or maybe y was at most the prediction, in which case this will be tau minus y times 1 minus q. Right, the quantity y minus tau or tau minus y, it's always just the absolute value of y minus tau, because we're just writing it in the multiplied by whatever sign makes it positive. Okay. And then so this is like a loss function. Like this is like the analog of just f of x minus y squared. And then when we evaluate the pinball loss, we want to take an expectation over a distribution. So given a data distribution D and a model, it's just any function from features to predicted quantiles, the pinball loss, PB sub Q, for target quantile Q, of the model on that distribution, it's just the expectation over a random point drawn from the distribution of the loss, the pinball loss, of what we get when we plug in f of x, the prediction, as the predicted quantile tau and the realized label. Okay, so like here, where previously we were looking at expected squared error, we've replaced squared error with this funny looking function. Okay, so what is this funny looking function? Like it's not that funny looking. Like let's think about the median when Q is 1/2. In that case, right, this pinball loss function is just absolute value. It's just 1/2 the absolute value difference between y minus tau. Right. Because, well, y minus tau when y is greater than tau, and tau minus y when y is less than tau, I can write that in either case as the absolute value of y minus tau, and Q here is just like uniformly 1/2. And then, right, so when tau is 1/2, this function kind of looks like this. It's kind of like a wedge. And then what's happening as we vary Q? Well, we're just like decreasing the slope on like one side of the function and increasing it on the other. So this is sometimes called like something like tilted absolute value function. As I like increase Q, I start getting functions that look like this. They just sort of start with the absolute value function, but then they kind of get tilted, right? And they're balanced when Q is 1/2, but you tilt it more and more and more this way. Yeah.
So the original idea, right, is like if you have some quantile, you are looking to say that like if things are if I told you that this probability is below the quantile, now so if it's above it, like I guess the thing I'm confused about is the second term here, because it seems like you're you're punishing them for having an incorrelated quantile.
Yes. Well, we're going to prove some stuff that might, we're going to prove some lemmas that are going to justify this choice, and we'll maybe answer your questions. But like, let's think about maybe intuitively what's going on, right? Like, we want to make this loss small, right? So you're right. Like, bigger numbers sort of correspond to punishments.
Yeah.
Now, if it's a continuous distribution, right? So like, you're generally not going to get it spot on, right? Like, you're predicting like some value that you're saying 90% of the time we're supposed to be below this value. And, like, you will be punished to the extent that your prediction was different than the label, right? Like, if your prediction was somehow like equal to the label, there's like loss 0. But the magnitude of your punishment differs based on whether you guess too big or too small. And basically that's because, like, when Q is 1/2, things are balanced. We expect you to be too big half the time and too little half the time. So the punishment should sort of be symmetric, to be the same if you're too big or you're too small. And that's kind of what's happening here when Q is 1/2. And then as we ask you to get, like, higher quantiles, 80th percentile quantile, 90th percentile quantile, we expect you to be too big more frequently than you're too small, and so the magnitude of the punishment should change.
I did a bad job.
Well, we're gonna maybe this will be clarified in a moment when we prove that the qth quantile is the thing that minimizes this.
Okay, so then maybe you don't have to answer that, you can answer it later, but I realize, like, I guess the confusion I have is the fact that the magnitude that you are off matters in the way that we're calculating loss. That you would imagine that if you were, like that, the actual amount that you're off from the threshold shouldn't matter, right?
That does, how much you're off by doesn't show up in the definition of a quantile.
Right, but it shows up in the loss.
That's right. But somehow, like, that's what. I think all of these questions will be answered when we prove the next lemma, basically, which is that the qth quantile minimizes this thing. But like, maybe to answer this with intuition that doesn't help so much, like, suppose we're like contracting again to elicit truthful predictions from a greedy weatherman. Like, what are the kinds of things we can contract on? Well, just the realization and his prediction, right? Because that's what we observe. So our hands are, but like, we can't in particular write a contract as a function of the correct 90th percentile quantile of the distribution, because we don't know what that is. So like, our design space is that we can write down some function of like y and tau. Yeah, I don't know if I have great intuition beyond the thing we're going to prove. Okay, it's good. Question? Okay. Let's see. So I'm gonna, for the next half hour or so, do some calculus, but I haven't like taken any calculus class basically in a really long time. And so I'm gonna do things that are, kind of sketchy, but I've shown these calculations to grad students who know more calculus than I do, and they claim that it's generally true. But what did you say? Yeah. I think everything I write down can be rederived with rigorous techniques. But apologies in advance. But basically, like, right, what is this function? It's a convex function that is differentiable everywhere except at this annoying pointy spot here. But I'm gonna like take derivatives of this thing. Exactly. That's right. So basically, the basic thing I'm going to rely on, right? Like the one thing I remember from like high school calculus, right, is if I have like if I had like a continuous convex function and I wanted to like think about the minimum, right? Like squared error, I'd want to look at the place where like the gradient was, or the derivative was 0. And for this thing, it's like a pointy convex function. Basically I want the minimum is going to be the place where there's a subderivative of 0. Now there's a bunch of subderivatives here. It's not differentiable at this point. But the minimum cannot possibly be at a place, a differentiable part of the function where the gradient is, where the derivative is non-zero. But I'm gonna ignore whatever are the appropriate words and like pretend I can take derivatives. Okay. So here's the claim. For any continuous distribution, over labels, and any target quantile between 0 and 1, let's consider a quantile that this like omniscient but greedy weatherman would tell us if we promised to pay him $1 minus his realized pinball loss. Okay, so he would choose, what would he choose? He would choose to tell us the thing that minimized pinball loss, because he wants to make as much money as possible. Right, so he would tell us some number that minimizes, among all such numbers that he could tell us, the expectation over the actual label distribution of this pinball loss quantity, given the number he tells us and the realized label. Right, so he's gonna tell us some number, we're gonna pay him some amount less this when the outcome is y, and he's risk neutral. He wants to minimize the expectation of that. Okay. As for any continuous distribution, consider the thing that minimizes this. The claim is that this is a Q quantile of that distribution. Okay, so this is the analog of what we proved in a more quantitative way. We'll have to get to the more quantitative version of this in a moment, which will be a little bit more complicated. But this is the analog of what we proved last class in a quantitative way about squared error. If you want to minimize squared error over a label distribution, you should predict the mean. Okay, the claim is if Q is 1/2, you want to minimize the absolute value error of a label distribution, you should predict the median. And more generally, for any quantile Q, if you want to minimize this pinball loss, this like tilted absolute value error, you should predict the Qth quantile. Okay. Yeah.
So when you say you should predict it, like this person who's giving you prediction, right? Is a reasonable way to think about it that they are seeing a sample data set that's representative of the true data.
Just 1 point.
Oh, okay.
Right. So this is an expectation over a single draw from this distribution.
So
the weatherman only sees 1 point.
The weatherman is, like a weather genius. The weatherman knows all about weather. But the contract that he's facing, by the way, like I didn't intend to go so deeply into this like game theory metaphor, which is not like super relevant. But yeah, the weatherman, right? He's like a weather genius. But like you've written a contract that pays off tomorrow. Tomorrow it's going to rain or not.
The principal only observes 1 point. The weatherman observes the distribution.
The weatherman observes the distribution. The principal, the guy who's employing this genius but greedy weatherman, only observes 1 point and desires to write a contract to elicit the Qth quantile of the distribution.
yeah, I guess I'm asking, right? So in this assumption, yes, the weather genius has full information about the distribution.
Yep.
But does this still hold if instead they had noisy information, like they had some expectation of what they thought the mean was and the median from, and then
the expectation is over their distribution. So this will, so long as they truly believe their distribution, when they're computing their payoff, they will compute this expectation over their distribution and they will report what they think is the Qth quantile. Okay. Okay, but like more generally, what I'm proving has nothing to do with like Weatherman or money. It's that if I take this function and I ask what minimizes it in expectation over y, the thing that minimizes it is the target quantile of the distribution. Okay. And this is very simple. It's just a couple of lines of slightly incorrect calculus. So, it's like a convex function. To minimize it, we should find a place where the gradient is 0. All right, so like it's not really differentiable everywhere, so we want to find a place where the subgradient might be 0, the subderivative. Okay. So let's look at the derivative of this thing, the derivative of the expectation over y of the pinball loss with respect to tau. We want to find the value of tau that minimizes this thing. Well, expectation is linear, so we take the derivative inside the expectation. And so this is the expectation of, well, this is a piecewise linear function, piecewise differentiable. So there's like two cases, either y is greater than tau or y is less than tau. So this is the expectation of the derivative of this thing. Now, if, let's see, write this with more space. If this is the indicator function, so I'm going to use notation like this now and in the future. This is just the random variable that evaluates to 1 when the event, that the Boolean predicate inside is satisfied. So this is 1 if y is less than tau, it's 0 otherwise. So in the event that y is less than tau, or in this case, in that case, the derivative of this linear function with respect to tau is 1 minus q. Okay. And in the remaining case, right, when we have the indicator that y is greater than tau, well, the derivative of this linear function with respect to tau is minus q. Okay. So note that like we're going to have this minus q term no matter what, because it shows up when y is less than or equal to tau, and it also shows up when y is greater than tau, and y has got to be either less than or equal to tau or greater than tau. So it's really just, whether y is less than or tau or greater than tau really just affects whether this 1 is here. Right, so this is just the expectation of the indicator that y is less than or equal to tau minus q, right? When y is less than or equal to tau, we have a 1. When it's not, we don't. And in either case, we subtract off q. And this is just the probability that y is less than or equal to tau minus q. Now, we need there to be a solution where this thing is 0, right? And to set this to be 0, we need that the probability that y is less than tau is equal to q. Okay. So this is minimized by predicting a qth quantile of the distribution. Okay. So we can think about now, right? So in some sense, this is now an analog of squared error. It's something that's minimized by a different distributional quantity, the qth quantile rather than the mean. And so we can start to think about taking a model that fails to satisfy marginal quantile consistency and fixing it up so that it does satisfy marginal quantile consistency. And, you know, like we sort of expect that the result is going to be that it's got lower pinball loss than we started. But so far, all we've shown is that, you know, like the pinball loss maybe will be like, you know, a little bit lower, but we'd really like it to be a lot lower. Okay, so we proved we haven't yet proven the analog of what we proved for squared error. For squared error, we sort of said, well, look, if something fails to satisfy alpha marginal mean consistency and we fix it, we'll improve the squared error by alpha squared. Right now, we haven't done that. Okay, but let's first think about, you know, fixing up a model. Okay. The question I want to ask is the following. Suppose I've got some model F that doesn't satisfy marginal quantile consistency. Okay, so F has marginal quantile consistency error alpha. Okay. Let's let delta be a number such that f hat of x, or such that the probability, the marginal probability, so the probability over both x and y drawn from the distribution, that y is less than or equal to f of x plus delta is q. Okay, and let's let f hat of x just be f of x plus delta. Okay, so f hat of x is designed to satisfy marginal quantile consistency. And just note that because we assumed the label distributions were continuous, there is such a delta, right? Like because it's a continuous distribution, as I continuously shift this function over by delta, I continuously change this quantity, and I can hit, you know, it's like, you know, definitely 0 when my threshold is like below the minimum of the range. It's definitely 1 when it's above the maximum of the range, and so there's a value that hits any target quantile q. Okay, I want to know, you know, like, is this enough information? So for squared error, right, we were able to say, okay, you know, delta is the amount you sort of had to shift by, or delta was sort of the amount you had to shift by to fix this marginal mean consistency error alpha. Now, in the case of means, delta was equal to alpha. If you had marginal mean consistency error alpha, to fix that, I had to like shift the model by alpha. But for quantiles, there's this disconnect, right? And so like, we need to make an assumption here if what we want to do is prove something that says f hat of x has much lower pinball loss than f of x, at least if alpha is large, right? Because the problem is, let me draw like the CDF of a label distribution. The problem is all of the action might be packed in a very narrow area. Maybe the labels, you know, maybe there's, you know, the labels, you know, like just never are below some value. And then all of a sudden we get into some very narrow range and it just shoots up like that. Okay, and so like basically, you know, all of the values between any reasonable quantile I care about, all of the thresholds for any reasonable quantile I care about, just live in some like very narrow range here. Right, so like the problem is, like, if the CDF of the distribution is just like super sharp, then it might be that even though I have very large quantile consistency error, like alpha might be close to 1, the fix that I need to make, like how much I need to shift the predictions to fix that quantile consistency error might be tiny, right? And if we look at pinball loss, you know, there's like this sort of term that is like linear in the shift that we're making. And so if we're making like just a tiny little shift, there's no chance that we can decrease the pinball loss by more than a tiny amount, right? And, you know, absent any other assumptions, the shift could be arbitrarily tiny. I could make this interval in which all of the action occurs, in which the CDF goes from 0 to 1, to be as narrow as I want, while, you know, having some continuous distribution, right? So that's the difference between like mean consistency, marginal mean consistency error, and marginal quantile consistency error. For means, my error in predicting the right mean, alpha, was the same thing as the shift that I needed to make, right? And these scoring functions, they can't be a function directly of the quantiles. They don't know the quantile. They have to be a function of the prediction and the realized label. And so these functions just aren't going to change very much if the prediction doesn't change much, right? So for means, there wasn't a problem. There was this direct connection between the scale of my error in predicting the mean and how much I needed to shift the model to fix it. For quantiles, that connection doesn't exist, right? Like in principle, I could have maximal quantile consistency error. I could be predicting something that, you know, is always lower than the label. So I've got like a 0 percentile quantile, but I could be infinitesimally close to my target quantile. Okay. So if we want to make a quantitative statement about how much lower the loss of the pinball loss of f hat is compared to f, we're going to need to make an assumption on the distribution, that the distribution cannot sort of increase basically too rapidly. Does that make sense? Okay. So here's our assumption. A conditional label distribution E of x is rho Lipschitz continuous, or I might just say rho Lipschitz, if for all pairs of thresholds, tau and tau prime, between 0 and 1, without loss of generality, assume tau prime is the bigger of them. If I look at the CDF of the label distribution, or rather I look at the difference between the probability that the label is less than tau prime compared to the probability that the label is less than tau. Okay, so this is like that jump in the CDF when we shift a threshold from tau to tau prime, right? How much does the corresponding quantile change, right? Like this is sort of the quantile of tau prime. This is the quantile of tau. This should be at most rho times tau prime minus tau. Okay, that the jumps should not be arbitrarily steep. But if I just wiggle the threshold a little bit, then I should just wiggle the quantile, the corresponding quantile a little bit as well, where, you know, if I've wiggled the threshold by blah, maybe I've wiggled the quantile by rho times blah, but not by more than that. So rho is some parameter that is giving us this connection we're going to need between how much we wiggle things in threshold space to how much we wiggle things in quantile space that otherwise is sort of the missing ingredient that we would need to make a quantitative assertion that pinball loss goes down substantially when we fix a large problem with marginal quantile consistency. Is it clear both what this condition is and means and why we need it? Questions? It's like a necessary condition, right? Because otherwise I could have, it's a necessary condition to proving quantitative statements about the decrease in pinball loss, because otherwise, you know, the fix to being arbitrarily off in terms of my quantile estimation could be arbitrarily small in terms of how much I need to wiggle my threshold. And, you know, like, here's the threshold. It's a linear function of the threshold. If I wiggle the threshold by at most epsilon, I'm not going to decrease the pinball loss by more than epsilon. Right? Sure.
I was gonna say, like, I understand like the problem, but I guess maybe I don't quite understand the form of the solution. I guess one can imagine like an algorithm that could do some sort of binary search to find the threshold that wouldn't have to make any guarantees. But you're trying to say like, oh, definitely if we move by this amount, and that's gonna help us. Like that's the statement you're looking for.
The kind of thing I want is the analog of what we proved for squared error and means. I want to say that if there's a big problem, if my marginal quantile consistency error is big, like for, you know, it's alpha for some large alpha, then when I fix it, I make some kind of big, yeah, how big kind of big is going to be mediated by rho here, some kind of big improvement in this loss function. And because, you know, the improvement can't be bigger than how much I've moved in threshold space, I need something connecting how much I need to move in threshold space to my error in quantile space. And that's exactly what this condition is doing.
It needs to be guaranteed regardless of the distribution, like conditional on these assumptions.
The thing we're going to prove next is if the distribution that we're interested in is rho Lipschitz, then if we have large quantile consistency error and we fix it, we will have decreased the pinball loss by some amount that depends on our quantile consistency error and rho. Make sense?
Something that I don't understand. So we want to fix a price kind of shift variable. In this definition, alpha, when f of x is always like, and it is always true, we might have large alpha. This wasn't true in squared error.
So say that again. So like f of x is always equal to y. Then this would be a very good predictor of the mean, but it would be a very bad predictor of the median of the label distribution in this marginal sense, right? So if, suppose there is no x, or let's see.
Always true. It should be a good predictor of everything.
So if f of x is always equal to y, then what you are predicting is like the 100th percentile quantile of the distribution. Like you're always predicting like an upper bound of the distribution. Now, this isn't going to be able to happen unless the distribution is sort of a point mass. So we run into some trouble in the definition of quantiles. But like what I want for a median, basically, is that half the time the realized label is below the threshold and half the time it's above. Right, so I don't want that it's like always above. Now, what you're referring to, in which like I always get it spot on, just can't happen unless the distribution's a point mass, in which case the definition of quantiles kind of breaks down a little bit. But yeah, but like for the median, right, like it should be that half the time you're too big, half the time you're too small.
Not uncertainty. There's no uncertainty.
Yeah. So that's right. So in order to avoid, like, for example, all of this discussion is under the assumption that the distributions are continuous. Otherwise, it's like not even clear what we're talking about when we're talking about, you know, medians and other quantiles. But yeah, uncertainty. Did you have a question? Okay. Okay. All right, so now let's prove under the assumption of Lipschitzness, sort of the quantitative version of this. Not only that this loss is minimized by predicting the correct quantile, but that if our model is like super off in getting its quantiles on average, then by fixing it in this simple way, by just shifting it to get marginal quantile consistency, we will have decreased pinball loss by some amount related to alpha and rho. Okay. So let's fix any rho Lipschitz distribution B. And any model F, which maps features to thresholds, that has marginal, quantile, consistency, error alpha with respect to some target quantile Q. Okay, and let's let f hat of x be as we defined before. It's just the shifted model, f of x plus delta. And let's assume we've chosen this delta so that f hat of x does satisfy marginal quantile consistency. Okay. Then the pinball loss of f hat is less than the pinball loss of f by an amount that we can relate to alpha, by alpha squared over 2 rho. Okay. And while we're messing around with quantities like this, why don't we prove a bound in the other direction as well? Because eventually we're gonna start to worry about like out of sample issues, and we're gonna be estimating quantities that aren't like exactly right. And we don't want that if our estimate is wrong by just a little amount, it totally, ruins our pinball loss. So let me prove sort of an inequality also in the opposite direction from this that'll be like useful to us later on, which is, this is saying the pinball loss decreases by a lot if we make a big fix. But it also doesn't decrease by too much. But it's also true that the pinball loss of f hat is bigger than the pinball loss of Q minus alpha squared over 2 rho plus the absolute value of delta alpha. So in particular, if we sort of wiggle the actual correction of the threshold by just like a little bit, then we won't drastically change the pinball loss. Yeah.
Is the property of a distribution being row Lipschitz easy to check for if I gave you some distribution?
If you can plot the CDF, it's just a bound on the slope of the CDF. And it's also easy to enforce. Maybe we'll talk about this when we get to quantile, when we get to conformal prediction. Suppose I've got some distribution that is a point mass or, otherwise really ill-behaved. I can perturb it. I could perturb it with an arbitrarily small amount of noise and turn it into a continuous distribution. And I could perturb it with an amount of noise that depended on rho and make it rho Lipschitz. Now there would be some cost to doing this in terms of the distance between the distribution that I'm analyzing, which now has nice properties, and the real distribution, but in a controllable way. So if we ever get ourselves into a scenario where we've made an assumption that our distributions are continuous or rho Lipschitz, and then we face a data distribution that's not, we can sometimes wiggle our way out by adding little amounts of noise to the observations.
Minus absolute value of
No, plus absolute value. You're right. It can't be bigger than something. Right. It's less than this, so it can't be bigger than something that is. I guess it could be. You think it should be minus? Let's see.
it's like less than this thing, and then you add it plus now you're saying that it's bigger than this.
I guess that does seem suspicious. So you're saying I've said it's like less than something. And then I've also said it's bigger than the thing that I've said it's less than. It does seem suspicious, yeah. Nevertheless, this is what I've written in my notes. So maybe we can pay attention as we prove it. Yeah, but yes, good eye.
I think in your note it's not this one.
Oh, okay.
Because on the left side.
Oh, yes. You have access to my notes. Good. Okay. Yeah. Okay. Yes, I should look at my notes more carefully. Happier with this? Okay, good. But my intention in all of this is that I've done all of the thinking previously and written it down, and that I can just seem smart by reading from what I've already thought. And so when there's evidence that there's something wrong with that, I get scared because I don't know how I'm going to recover because everything else. But I'm glad it's correct in the notes. Okay. Okay. So I'm again going to do a bunch of shameful pseudo calculus. Apologies in advance. But again, people who know calculus say that you can utter the relevant incantations and make all of this rigorous. Let's see. I think I want to keep this. Okay. I'm going to think about derivatives again. So we can sort of reuse this calculation. Right, so the derivative of the pinball loss of f of x plus tau with respect to tau. Well, the pinball loss, remember, is the expectation of this loss function. So I can take the derivative inside the expectation. It's just the expectation over x of the derivative of the expectation over y drawn from the conditional label distribution given x of this pinball loss function LQ evaluated at f of x plus tau and y. Derivative is with respect to tau. Okay. And we already helpfully calculated this derivative over here. So this is just the expectation for x of the probability over the label distribution, the conditional label distribution of f of x plus tau. Sorry, the probability that y is less than or equal to x plus tau minus q. Here I'm just reading off the result of our previous calculation, which is just the probability over the whole distribution that y is less than or equal to f of x plus tau minus q. Okay. Now, the thing that I am interested in is the difference between the pinball loss of f hat, which is just f of x plus delta, and the pinball loss of f of x. Okay. Right. This is the thing I'm interested in bounding. How much does the pinball loss change when I shift the model by delta? Okay. So this is just the integral from 0 to delta of the derivative of the pinball loss of f of x plus tau with respect to tau. Right, because if I take the derivative, sorry, if I take the integral from 0 to delta, I take the like antiderivative of the integrand, which is just the pinball loss. I evaluate it at delta, and then I subtract it off the antiderivative evaluated at 0. Okay, so I've written this difference as an integral. Okay, but we know what this derivative is. So this is the integral from 0 to delta of the probability that y is less than or equal to f of x plus tau minus q. Okay, because that was the value of the derivative. And now there's maybe like two cases we might want to keep track of: the case when delta is positive and the case when delta is negative, right? Because we might have like shifted the model up, delta is positive, or we might have shifted the model down, delta is negative. And so this is, well, either the integral from 0 to delta of the probability that y is less than or equal to f of x plus tau minus the absolute value of delta times q if delta is positive, or plus the absolute value of delta times q if delta is negative. Right, because either way we get, we're taking the integral from 0 to delta of minus q, we get minus delta times q, but like that's plus the absolute value or not, or minus the absolute value, depending on the sign of delta. Okay. Okay, so this is an expression we can sort of try to understand, right? Like this is something that's asking us about the area under the CDF of this label distribution, right? So, right, we can write down the CDF of a label distribution, and if delta is positive, then this thing evaluates to the area under the curve of that CDF as we range tau to like from 0 to delta. Okay. And if delta is negative, it's just the negative of the area under the curve. Okay. So what we need to do is we need to sort of understand the maximum and minimum area under the CDF as we range tau from 0 to delta under this Lipschitz condition in order to get bounds on this integral. Does that make sense? Okay. So let's draw a picture. So on the x-axis, I want to draw tau. Okay, and let's consider the case where delta is positive first. So, we're interested in the area under the curve, under some curve of some CDF between tau equals 0 and between tau equals delta. Okay. Now the y-axis will be the probability that y is less than f of x plus tau. So what's going on the y-axis as we vary tau from 0 to delta? Well, we know that initially, when tau is 0, and we just have our model f of x unmodified, that this model by assumption had quantile consistency error alpha. And to fix it, we shifted it upwards by delta. So when tau is 0, the probability that the label is less than f of x, even though we were hoping it was q, was actually q minus alpha. Right, so that's what it means to have quantile consistency error alpha if you're underestimating. And then we start shifting it upwards until we get to delta. Well, why did we stop at delta? It was because finally it satisfied it had perfect quantile consistency, right? So that means by the time we shifted it up to delta, the probability that the label was less than f of x plus tau was exactly q. That's why we stopped there. Okay. And so we'd like to sort of understand what this sort of CDF-like curve might look like to sort of upper and lower bound the area under the curve. Now our concern, like if the thing wasn't Lipschitz, our concern is that like, it could just jump like straight up basically to maximize the area under the curve, and to minimize the area under the curve, it could jump straight up at the end. But under our Lipschitz assumption, it cannot do that. If the CDF is row Lipschitz, then like the rate of increase cannot be larger than rho. And so if it's got a hike all the way from Q minus alpha up to Q, in the worst case, it's like, like coming up against its like Lipschitzness constraint. It's doing so at some linear rate, right, with slope rho, and it finally makes it up here after we've shifted the threshold by alpha over rho, right? Because it's got to travel alpha on the y-axis, can't do it faster than a rate of rho, so it's going to take it to at least alpha over rho on the x-axis. Okay, and CDFs are monotone, so it can't go up and then down. So, like it's gotta, if it did that, it's gotta stay constant here until it gets to delta. Okay, this is sort of like the worst case CDF for maximizing the area under this curve. Okay, and we're interested in computing this worst case area under the curve. Okay. Well, we want to bound this integral, this area under the curve, right, between tau is 0 and tau is delta of the probability that y is less than or equal to f of x plus tau. And, I guess we can like break this up into like a big rectangle and a little rectangle and a triangle. So let's start by computing the area of this big rectangle here. The base has length delta minus alpha over rho, and the whole thing has height q. So this is just delta minus alpha over rho times q. Then we've got to add in this little rectangle here, which has base length alpha over rho and height q minus alpha. And then finally, we've got this little triangle here that has base alpha over rho, height, I guess alpha, and it's a triangle. So we multiply base times height and divide by 2. So plus alpha over rho times alpha over 2. And we get q times delta minus alpha q over rho plus alpha q over rho minus alpha squared over rho plus alpha squared over 2 rho, which I guess equals q times delta. These terms cancel out. We get cancellation here. So minus alpha squared over 2 rho. And the whole thing we wanted to bound when delta was positive was this integral, which is q delta minus alpha squared over 2 rho minus q delta. And so the q delta cancels out. And so at least in the case in which delta is positive, we conclude that the difference in pinball loss between our fixed model and our original model is, well, Q delta minus alpha squared over 2 rho minus Q delta, which is just minus alpha squared over 2 rho, which is what we wanted. Okay. So we now want a lower bound. Sorry, so we just figured out like what is the maximum possible area under this curve under our Lipschitz assumption. To prove the bound in the other direction, we want to figure out what is the minimum possible area under this curve. Right? And again, we know that we start at Q minus alpha. In quantile space, we end up at Q. We start at 0 in threshold space and end up at delta. Our curve has got to be monotone and it's got to obey the Lipschitz constraints. So what's the worst thing that can happen to minimize the area under the curve? Well, it's that the CDF stays constant at Q minus alpha for as long as it can before at the last minute jumping up to Q as fast as it can, but it can't head upwards faster than a rate of rho. That's the Lipschitzness assumption. So it's got to begin its ascent at delta minus alpha over rho. That's like the last moment at which it can hold the fort and stay down at Q minus alpha. And so what's the area under this curve? Well, I guess we can break this up into kind of a skinny rectangle and a triangle. And so we can also, in a sort of similar geometric way, notice that the integral between 0 and delta of this CDF-like quantity, the probability that the label is less than f of x plus tau, well, it's at least the area of the skinny rectangle, which has base delta and height Q minus alpha. And the area of that triangle, which is alpha squared over 2 rho. Right, so this is delta Q minus delta alpha plus alpha squared over 2 rho. And again, plugging it into our bound, we get that the change in pinball loss between f hat and f is at least delta Q minus delta alpha plus alpha squared over 2 rho minus delta Q, which is just alpha squared over 2 rho minus delta alpha. Okay, and I won't subject you to the case when delta is negative, which is very, very similar, but delta is negative. So it's 3:15. You guys want to take a break? Yeah. All right. Should we say like a 10-minute break? So come back at 3:25. Okay. So let's carry forth. We almost have an analogous set of results for quantiles now compared to what we proved last time for means. There's just one like little thing missing, right? What do we have so far? We've got well, a definition of quantile consistency. We've got a theorem that says if we don't satisfy quantile consistency, then it's easy to fix it. And in doing so, we make progress, at least according to pinball laws. At least, and that progress is like quantitative, at least if the distribution is Lipschitz. But one thing we proved last time for means was that, you know, even though we analyzed everything as if we had access to the underlying distribution, like in that we could actually compute expectations, we didn't really need that, because if we had an IID sample from the distribution, that was good enough. If we satisfied mean consistency, marginal mean consistency on a sample of data that was drawn IID from the distribution, then we were approximately mean consistent, marginally mean consistent on the distribution. So let's just pin down that statement for quantiles as well. And the main purpose of going through this, just as the main purpose of going through it last time, was to introduce Hufting's inequality to you, which is going to be sort of like a workhorse in general, as we try to, for more complicated guarantees, transition between what a machine learning person might call in-sample versus out-of-sample guarantees, like empirical quantities computed from data compared to quantities evaluated on the underlying distribution. When we want to do that for quantiles, there's a sort of analogous probabilistic statement called the DKW inequality, which I will quote for you in proving this little lemma. But, you know, more important than the lemma probably is just that you remember the existence of the DKW inequality, which is generally a useful probabilistic tool. Okay. So what's our theorem? What's our first statement about connecting in-sample to out-of-sample quantities when it comes to quantiles? Well, let's fix a model F and any distribution D. And let's say that D without the squiggles consists of n samples from the distribution D with the squiggles sampled IID. Okay, in particular, again, these had better be sampled after we pick the model, or at least independently of the model. If we train, if the model depended on the samples, like we trained the model on the samples or something, this theorem wouldn't hold. And let's let delta be such that sort of the shifted model of the sort we've been talking about, f of x plus delta, has, well, has marginal quantile consistency error alpha prime with respect to target file Q, not on the distribution, but on the data set. Okay, so we've performed this shift to fix up F, not on the underlying distribution. We don't have that, but on this empirical sample. And note, I didn't say, perfect marginal quantile consistency error 0. On the sample, we're actually not guaranteed to be able to do that, because if we had a nice continuous distribution, we could sort of continuously choose a shift delta until we got exactly the qth quantile. But on an empirical distribution, the distribution is sort of like a step function, right? Like if I have only n samples, then I'm not guaranteed, it doesn't even make sense to talk about quantiles that aren't multiples of 1 over n, right? Like if I have only 2 samples, how are you going to take the 33rd percentile of this thing? Okay, so like it's important that we be able to talk about things that are like, kind of quantile consistent, but maybe not like perfectly quantile consistent if we're talking about doing this on samples. Okay. Then the claim is that with probability 1 minus delta, this is over the randomness of the draw of the data set. Okay, with probability 1 minus delta over the sample data points, f hat has marginal quantile consistency error alpha with respect to target quantile Q on the underlying distribution, the real thing, not the sample, for alpha that is no more than alpha prime, what we had on the data set, plus the square root of log 2 over delta over n. Okay, so we have the same sort of quantitative thing that we had for means, which is that our estimates on the sample are sort of true to the distribution with error that drops off at a rate of 1 over root n, which is sort of the right thing, right? If I sort of flip n coins, I expect to have like, standard deviation around the mean that's on the order of 1 over root n, and that's what we're getting here. Okay. Okay. So this is an application of a standard concentration inequality that you should all know, called the DKW inequality, which stands for Dvoretsky, Kiefer, Wolfowitz, but that I will call DKW to save on chalk. Okay. Let me quote for you the DKW inequality. This is probably not the first time we will use it. More useful to you than remembering the actual lemma we're proving is to remember what the DKW inequality is, which is the tool we're going to use. Okay. So let D be any distribution over labels. And let D without the squiggle be a sample of n points drawn IID from this distribution. And let's let f of c be the true CDF of the distribution. So f of c is the function that says, well, it's the probability that the realized label is less than or equal to c. It's just the CDF of the distribution, the thing we don't know, but we've got samples from. And similarly, let's let f hat of c, which is parameterized by our sample, f hat of c computed on the distribution, be its empirical counterpart. Okay, so this is just fraction of points in the sample such that the realized label is less than or equal to c. Right, like this is like the empirical version of the CDF. Okay. Then what DKW says is that the probability that the empirical CDF differs from the true CDF anywhere. This is sort of the difference between this and just Hufting's inequality. This is going to be a uniform statement over all of the like, infinitely many points at which we might evaluate the CDF. So I'm going to take the supremum over all values C of the difference between the real CDF value at C and the empirical CDF value at C. The probability that these 2 points differ anywhere at any value C by more than T is at most 2 times e to the minus 2 nt squared. Okay, so this is sort of like what what Hufting's inequality looked like, the probability that we see some deviation from our expectation by more than T sort of drops off exponentially with T, faster and faster as we have more samples. Right, again, right, like at any particular point C, the expectation of f hat of C is equal to f of C. So this is sort of saying that the realized value won't differ from the expectation by too much. But like the thing that's more powerful here that you couldn't derive just from Hufting's inequality is that we're not saying this just for one point C, we're saying it uniformly for all of them. Okay, so it's saying like, if you're interested in the CDF, then you don't need very many points before the empirical CDF is point-wise close everywhere to the real CDF. Okay.
This is a univariate CDF.
This is a univariate CDF. So this is a statement about one-dimensional quantities. But I imagine that there are analogs for.
It's on the right side, it's 2K, with K being the number of values.
2K here. And yeah, actually, wait, what is?
If it's a multivariate CDF.
Remind me, what is a multivariate CDF?
The 2 times integral of 2 variable integral.
Like, what is the analog of being like less than something in higher dimensions?
Something, y less than something.
Okay, so like being dominated in every
Yeah.
coordinate. Got it. Okay, cool. So there's a higher dimensional analog. Yeah. Now in this class we will mostly be thinking about one dimension. Okay. So okay. So internalize love the DKW inequality. Once you know that, it's very easy to prove this. Okay, in particular, like we just have to figure out what distribution we should be talking about. Right, so let's let this new distribution d prime be derived from D by replacing the label of an example xy with a new label, which I'll call y prime, which is just y minus f of x. Okay, this is some new distribution over labels. I'm going to apply DKW to that one. Okay. Right, so by definition, right, what is delta? Well, we know delta was chosen so that the probability over a draw from our original distribution that y is less than f of x plus delta deviates from our target quantile q by alpha prime. And with you know, under our new distribution here, to which we want to apply the DKW inequality, writing this is just the claim that the empirical CDF on our sample of delta differs from Q by at most alpha prime. This is just the empirical, sorry. This is on our sample. This is the empirical CDF of this like relabeled distribution on our sample. Okay, so now we just apply DKW.
Or what's that symbol up there?
Which one?
For the absolute value.
Q. Yeah. Yeah, I guess right. I can't blame it on the camera resolution, but it's possible you can't read the board even in person. So let me know. Those of you watching from home here, people suffer the same problem. Okay. So we just have to apply DKW. We want the right-hand side to be at most delta. So we just choose T so that this evaluates to delta. That's just T equals root log of 2 over delta for 2n. And we get that the true CDF of this distribution D prime evaluated at delta minus Q, right? So just swapping out the empirical CDF for the true CDF, which we can do at a cost of the error bound that DKW gives us. Well, it's at most what it was for the empirical CDF plus the error bound, which is this. This holds with probability 1 minus delta. Okay, and just expanding this all out, we've got that alpha prime plus the square root of log of 2 over delta over 2n is at least the difference between the probability that y minus f of x is less than delta minus the target quantile which is just the probability that y is less than f hat of x minus the target quantile, which is what we want, right? Then we have that alpha plus our error term, which goes to 0 at a rate of 1 over root n, is equal to the quantile consistency error of our model now out of sample. Okay, makes sense. So same kind of application of a concentration inequality, similar to how we moved from in and out of sample bounds for means, but along the way we learned the DKW inequality. Okay. Questions about any of that? Okay. So what I want to do now is shift from the batch setting to the sequential setting. Okay, and just to sort of maybe remind you of some of the roadmap that we went over last class. Right, there were sort of two things about the roadmap we talked about, like, okay, one, we already went over earlier today that sort of our goal is to build up more and more stringent tests aimed at falsifying that models are not representative of the true conditional label distribution. And so far we've done sort of the weakest possible test, both for means and quantiles. And one of the agendas of this class is going to be to build up more stringent things. But everything we've done so far is in the batch setting, meaning we've assumed there's like a distribution over data points. All of our goals are defined with respect to that distribution. And we've been proving these theorems with things like Hufting's inequality and DKW inequality that sort of say, look, if you've got a sample that is representative of the distribution and you fix up your model to look good on the sample, then you will also look good on the underlying distribution. This is, of course, under the assumption that your data was representative of the underlying distribution, that your sample was correct, that it was IID, and that the underlying distribution did not change. Now, that will not always be true. It might be that you are trying to make predictions in a setting where maybe the distribution is changing in unanticipated ways, or maybe there isn't even really a distribution. Like maybe it doesn't make sense to model things with a distribution because observations are being generated by the strategic actions of people, for example, right? So things could change in lots of different ways. And another goal of this class is to try to see to what extent the things we can do, assuming that there is a distribution, we can also do in the more difficult setting when there's not a distribution. Okay. So, okay, so that's like a pattern that I'm going to follow for a little while. I'm going to like try to do something if there's a distribution, and then we're going to see if we can do the same thing without a distribution. Okay, so far, what have we done with a distribution? We've shown how to satisfy marginal guarantees with respect to means and quantiles. Okay, so now I want to ask, suppose we are in the sequential setting. Remember, what is the sequential setting? Every day we see X. Then we have to predict something, maybe something that purports to be a mean of the label distribution, whatever that means. There's no distribution anymore, but I can still purport to speak of it. Or maybe I purport to speak of a quantile of the label distribution, except there is no distribution, right? So in particular, like we can imagine, oh, and only after I make my prediction do I see Y. And then the next day occurs and I have to repeat this for tomorrow's X and Y pair. And my goal is going to be to like come up with an algorithm that promises that I satisfy whatever statistical consistency property I set out to satisfy on the empirical transcript of sort of what happens. Like after the fact, I do have some empirical distribution on XY pairs, the things I actually happen to see. And so I can ask things like, did my prediction satisfy, for example, marginal mean and quantile consistency on this empirical distribution? And I'd like to design algorithms that can promise that this will be the case in the worst case over adversaries. I don't want the adversary. I don't want to assume anything about the adversary, so that like when I go out into the world and deploy my algorithm, I don't have to worry that my assumptions are wrong.
When you say that there's no distribution, there's only that day by day.
So you can literally think of this as a strategic game against an adversary, where I will write down on the board in a moment like the definition of like marginal mean consistency on an empirical transcript, for example. But you can think about it as a strategic game against an adversary where like it's a T-round game. They are trying to pick X's and Y's that will cause, for example, at the end of time, my marginal mean consistency to be really high. I'm trying to choose predictions that will cause it to be really low. And I have to have algorithms that are so playing against an adversary is like playing a zero-sum game. And so like the adversary might be max min optimal. I might be, and I'm hoping for something that's min max optimal, and I'm hoping the value of the game is in my favor. Does that make sense? So there's no distribution. It's like, think of it as a strategic game against like an opponent. So it's a demanding model, but it's not, like remarkably, you can do lots of things in it. As we'll see, actually, for these marginal quantities, it's like super easy. Like the algorithms are going to be super dumb. And okay, this is both a reminder that these marginal quantities are not asking for much. Like we really should start asking for things stronger than marginal guarantees, but also maybe giving you a hint that even though this sort of adversarial sequential prediction setting seems really hard to deal with, it's not that bad. Okay, there's that, yeah, sort of remarkable how much you can do in the strategic, so in this adversarial sequential setting, and how much the results mirror what you can do in the distributional setting. Okay. So, questions about that before I like define some stuff? Okay, so remember how the sequential setting works. At day 1, I see feature vector x1. I make prediction p1. Then I see label y1. Then comes day 2. I see feature vector x2. I make prediction p2. Then I see label y2. And this happens for t days. And the record of all of these things that happened, I'm going to call a transcript. Okay. So let's fix a transcript. I, which is nothing more than the collection of 3 tuples consisting of the feature vector xt, the prediction pt, and the label yt that were realized in this interaction over all of the rounds from t equals 1 to capital T. Okay, so just a recording of this interaction with the adversary that defined the sequential model. And let's assume, right, like the XY pairs come from our feature and label space. And let's assume we're solving regression problems, so it makes sense to talk about like means and quantiles. And let's imagine that we've scaled everything again so that the labels are between 0 and 1, so it makes sense that our predictions are also numbers between 0 and 1. Okay, so the transcript satisfies marginal, mean, consistency, error alpha if, well, like there's no distribution before the fact, but like after the fact, after I've interacted with the adversary for t rounds, there's an empirical distribution over the rounds of the transcript. And so I'm just going to ask for marginal mean consistency over that empirical distribution. So in particular, if the difference between the average over the t rounds of interaction with the adversary of the predictions differs from the average over the t rounds of interaction with the adversary of the label by alpha. Okay, so I can ask, I can sensibly speak about marginal mean consistency in the sequential setting. There's no distribution anymore before the fact, but after the fact, I can look back at history now realized. And I can look at the empirical distribution of that history. And I can say, how close am I to being marginally mean consistent over this history? Now, again, why would you want this? Well, suppose we're in some sequential interaction, and maybe there's some underlying probabilistic process related to the features that is just complicated. We don't understand it. Okay. If someone, right, so it's weather prediction on Pluto. We don't know what's going on, but there's some guy who claims that once he sees the meteorological readings xt, that he actually knows the distribution of Plutonian rain and can tell us the mean pt. Well, it's hard not understanding weather on Pluto. It's hard for us to understand the mechanism, but if he's correct, then we can't evaluate anything over the distribution. But if he's correct, then after we've seen him make predictions for T rounds, in particular, he will satisfy marginal mean consistency. So if he doesn't, then we can identify him as a charlatan. Okay. Maybe the distribution's changing every round, but he knows what it is. The true conditional label distribution would satisfy marginal mean consistency. So we should check for that and wonder whether that is a sufficient procedure to call him out as a charlatan. We can just as easily define marginal quantile consistency in the sequential setting. So similarly, phi satisfies marginal quantile consistency with error alpha if the empirical distribution on the transcript is marginally quantile consistent. So in particular, just looking at the empirical average over the days of the frequency with which the labels were less than the predictions and how much that deviated from the target quantile. If that's alpha, we'll call it alpha, or satisfying marginal quantile consistency with error alpha. Okay. Now, it's a little bit less clear how to do this in the sequential setting than in the distributional setting. In the distributional setting, if we had direct access to the distribution, it was sort of clear. You could predict just the mean of the distribution, and from data you could compute the empirical mean. The kind of theorem we want now, since there's no distribution, says in the worst case over adversaries, uniformly over any sequence of x's and y's that might be realized, we would like algorithms that are, in this case, what is a sequential algorithm? Well, it's a mapping from sort of a prefix of a transcript, from the first k rounds of the transcript to a prediction at round k+1 that has the promise that no matter what the realized sequence of outcomes, it'll satisfy, for example, marginal mean consistency. Okay, so it's it's this universal quantifier that means we are competing against an adversary. We have to satisfy this simultaneously for every possible realization of transcripts. Okay, so that sounds kind of hard. Can anyone tell me how to do it for marginal mean consistency? Someone who does not have the notes open in front of them. Exactly. Yeah. So the algorithm that is going to achieve this remarkable guarantee against an adversary is super dumb. And the fact that it is so easy to achieve even against an adversary, you should maybe take as evidence of two things. Maybe one, that these marginal guarantees are very, very weak. but also two, maybe adversaries aren't that scary. Okay. So yeah, so suppose you have this weather predictor on Pluto, and you are trying to convince me that you really understand Plutonian weather, and I'm unconvinced, but also not that clever, and so I've decided to test you just by measuring your marginal mean consistency. And you actually don't know anything about weather on Pluto, but you would like to come up with a strategy that's guaranteed to pass this test. Well, what you could do is just predict that what's going to happen today is whatever happened yesterday. So if it rained yesterday, you say 100% chance of rain tomorrow. If it didn't rain yesterday, you say 0% chance of rain tomorrow. And that's it. Okay, so this is not a very good algorithm, but it's not a very good algorithm in general, but it is a very good algorithm for promising marginal mean consistency.
So this only works if the chance of rain in Pluto is actually random, because if it rains one day and if it's 0-1 one day after, then you're going to get 100% wrong. I mean, if there's a
But marginal, no. But marginal mean consistency does not require that you get it right on any of the days. It requires that on average, the frequency with which you predict rain
is the same.
Exactly. And by the way, like, this is a relevant line of thought as we go further in this class. Suppose our goal is to check whether someone knows what the distribution is. Checking whether they get the answer right is not in general a good way to check, because if the distribution is actually high entropy, like if indeed on Pluto every day it rains with probability 1/2, then even the guy who like really knows Plutonian weather is going to get it right half the time. So the fact that like you get it right, the fact that you rarely get it right does not falsify my claim that I know what I'm doing. Yes, so like the procedure that we're gonna think about will often get it wrong, and there will be, and maybe we'll think about this for a moment. This is going to motivate calibration as a strengthening of this marginal mean guarantee to be like a slightly more clever way to call out fraudulent Plutonian weather forecasters. But to satisfy this guarantee, you don't have to be right ever. Okay. Let's call this algorithm online marginal mean predictor. Okay, so let's say I'm going to hallucinate. Yeah, time starts at day 1, but I'm going to hallucinate that there was a day 0 and pretend that at day 0 it did not rain. Okay, these don't have to be binary, by the way, so we could be predicting inches of rain or something. Okay, now we operate in this sequential setting. So time proceeds in rounds from 1 to capital T. And we get to observe the features for that day. I get to look up the readings from all of the weather balloons I have on Pluto and all of the thermal vents that I've put sensors in and everything else. Okay, I get to observe all that stuff. And I will just throw it away. I will ignore it. Garbage, don't need that stuff. Okay, I will predict that what's going to happen today is exactly what happened yesterday. Okay, and then I'll observe what happened today. Okay, so if it's like inches of rain, then I'm going to predict the number of inches of rain today is equal to the number of inches of rain yesterday. If it's the probability of a binary outcome, if it rained today, I will predict a 100% chance of rain tomorrow. if it did not rain today, I will predict a 0% chance of rain tomorrow. Okay. All the while, like throwing away the meteorological information available to me. And like, despite the fact that this is on its face a terrible algorithm, good for nothing, it is very, very good at satisfying marginal mean consistency. In particular, it can do it even better than we could do it if we had a distribution, right? Like if we had a distribution and we had t samples from it, and we tried to like honestly estimate the mean, like the kind of error bounds on the true distribution that we get from Heffting's inequality sort of would have error on the order of 1 over root t. But unburdened from a distribution, we can get error on the order of 1 over t by this. Okay, so here's the theorem. For any sequence of examples, xt, yt, of length t, this algorithm, online marginal mean predictor, well, it's a deterministic algorithm. There's no randomness here. Deterministically produces a transcript that satisfies alpha marginal mean consistency for alpha at most 1 over t. We're really mean consistent, more than if we had tried to do this from a statistical estimate of data. Okay. And it's pretty easy to see, right? Like, what's the one thing to know about this algorithm? It predicts what happened yesterday, right? So because I predict today what happened yesterday, and in particular, I pretended that on day 0, the outcome was 0. When I look at quantity of interest, when I care about marginal mean consistency, the difference between the average of the predictions I make and the difference, and the average of the outcomes, I get this telescoping sum. The predictions are just yesterday's outcome. And so every term cancels out except the very first term, y0, and the very last term, y capital T. Right, so this is just one over t times the absolute value difference between y0 and y capital T. And y0 is 0. Y capital T is a number between 0 and 1. And so this is at most 1 over t. So if I was foolish enough to hire my Plutonian weather forecasters on the basis of marginal mean consistency, I could very well hire one who really doesn't know anything about Plutonian weather and is sort of skating by, like, hardly thinking at all, not even looking at the meteorological forecasts. Yeah. Yes. Well, this is the marginal mean consistency error, exactly, and it's less than 1/t. Yeah, so let's see. Can anyone think of anything else any other tests I might subject my weather forecaster to? Might be harder to pass. Yeah, it would be great. But like, if I say like, look, I'm only going to hire you if you always get it right. Like, you have to give me deterministic forecasts about like whether it's going to rain next week. I'm going to not get to hire any weather forecasters, even the ones who know what they're doing. So it'd be great if we could ask people to be right, but like, that's different than knowing the distribution. The distribution might be inherently stochastic, and so sometimes, yeah. So maybe we could ask them to be right sometimes. Yeah, once. Well, it's not hard to be right like half the time. I can always just like flip a coin if it's like a rain outcome. And there are distributions for which, even if I know the distribution, I can't be right more than half the time.
That's a good thing to add to anything, then, right? Like you should be right half the time.
Yeah, so if it's a binary prediction problem and you're right less than half the time, then that's a bad sign. It's a red flag. Yeah. So I could say, okay, like my test is I want you to be right half the time, but then you could start flipping coins. So maybe this is like a question that you should keep in the back of your mind as this class proceeds. Like, are there any tests out there that I could use to try to like, you could try to be like really clever. And I want that these tests should actually pass people who know what they're doing. Like they should be fair tests. So I want that the tests should like not fire the Plutonian weather forecasters who really like went to Plutonian meteorological school and like know what's going on, but that also like require that like also shouldn't be able to be passed by like an algorithm like this that like has guarantees for arbitrary sequences, because if there's an algorithm that can pass the test for arbitrary sequences, then clearly the test is not indicating whether you know anything about the governing distribution. Okay, so maybe that's a good question to keep in the back of your mind. Like we just showed that like mean consistency is so weak that it doesn't have this property, but is there anything else? All right, and let me give you the time back and we'll keep talking about these things next week.